Asymmetrical Multilevel Inverter with Low THD. Abstract Multilevel Inverter is a new family of converters for DC-AC conversion for medium and high voltage and power applications. In this paper, a new topology has been proposed with lesser number of switches for the generation of nearly sinusoidal output voltage 1. This is an asymmetrical 15-level multilevel inverter topology with less number of switches. The THD of the output across the load is less, which promotes to better activity of the inverter, and as a result overall efficiency of the system increases. The output results and FFT analysis of asymmetrical 15-level multilevel inverter topology are ascertained by utilizing MATLAB/SIMULINK software. Index terms: MLI, asymmetrical, pulse width modulation technique, switching scheme, total harmonic distortion. Introduction. As of late, the propensity to produce power from renewable energy sources is expanding. Simultaneously, the power rating of photovoltaic power plants, wind turbines, and renewable equipment expanded quickly. A circuit which changes over DC power into AC power at wanted output voltage and frequency is an inverter. The AC output voltage could be fixed at fixed or variable frequency. The controlled turn-on and turn-off or by constrained commutated thyristors relying upon the applications could achieve this change. Thyristors should be utilized for high power output. For low and medium voltage applications, square wave or quasi-square wave voltages might be adequate, and for high force applications, low distorted sinusoidal wave structures are required. For this low distorted sinusoidal wave structures, staggered inverters are utilized, as they produce almost sinusoidal waveform which has low THD and low dV/dt proportion, which will be more in a conventional inverter for. Because of the popularity for medium power converters and high. The configuration of proposed topology is shown in Figure 1. Dr. K. Ramasuda, Professor, Department of Electrical Engineering, Andhra University College of Engineering, A. Visakhapatnam, Andhra Pradesh. Power converters. Staggered inverters are a convenient and intriguing test with regards to the field of intensity hardware. 3. The zones of enthusiasm for the present analysts are the new staggered topologies that can give lower THD and high productivity, particularly at high force levels. New thoughts and research have been given and inquired about by specialists. The progression in the field of intensity electronic has improved the use of high-power medium voltage drive applications in the mechanical field. The dV/dt and the harmonics should be limited by the presentation of more levels in the yield voltage so as to show signs of improvement execution of medium voltage and high-power electric drive. 6. The output voltage produced from the multilevel inverter is at high frequency and low switching frequency with low distortions. 2. Proposed topology. The proposed topology is modeled so as to acquire lesser THD with reduced number of switches for 15-level multilevel inverter. This topology requires 3 DC voltage sources and 13 switches to synthesis 15 levels across the load. This is an asymmetrical 15-level MLI topology using sinusoidal pulse width modulation technique. In this asymmetrical MLI, the DC source magnitudes are unequal and it is designed by binary form of voltage such as VDC to VDC and 4 VDC. The THD of the output waveform decreases as the number of levels increases. The overall efficiency of the system increases as the THD of output across load diminishes. This prompts the better activity of inverter. In this topology, the THD of the system is very much reduced. 3. Circuit diagram. Fig.1 circuit diagram for the proposed topology. 4. Switching scheme. Pulse width modulation, PWM, is a modulation technique utilized in most communication system for ciphering the amplitude of the signal write width or duration of another signal, usually a carrier signal. A multilevel inverter control scheme can be classified according to switching frequencies as fundamental switching frequency control and high switching frequency PWM control. The sinusoidal pulse width modulation technique is generally well known among all and broadly utilized in modern applications too. It is basic and more adaptable than SVM technique. SPWM technique uses several carrier waves and one reference wave per phase. The number of carrier waves used will be N1, where N is number of levels. The switching strategy comes under level shift pulse width modulation technique. The SPWM level shift can be further classified as 1. Phase disposition, SPWM-PD. 2. Phase opposition and disposition, SPWM-POD. 3. Alternate phase opposition and disposition, SPWM-APOD. Advantages of multi-carrier PWM techniques. 1. Easily extensible to high number of levels. 2. Easy to execute. 3. To distribute the switching signals accurately so as to limit the switching losses. 4. To compensate unbalanced DC sources. Out of these techniques of SPWM we have used phase opposition and disposition technique in the switching scheme to trigger the gate circuit as it has most reduced line-to-line harmonic voltage distortion is achieved by it. To build a 15-level output waveform through the LS-SPWM strategy 14 carrier waves are required. Here in this, positive 7 carrier waveforms are out of phase with negative 7 carrier waveforms. The switching sequence for every 13 switches utilized in switching pulse for S5. By utilizing this topology, the number of levels synthesized can be increased by increasing the No of sources. As the number of levels increases, the No of switches used also increases. The higher the No of levels, the lower the No of switches used for synthesizing these levels compared with IJERT 9 is 050540 www.ijert.org. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org ISSN 2278-0181. Volume 9 Issue 05, May 2020. The No of switches used for the lower levels 5. Generalized formulas have been proposed for these topologies for obtaining the voltage levels and the No of switches used as the No of sources increased. In this manner, the number of levels that can synthesized using the proposed topology is n equals 2, n plus 1, minus 1, 1, where n represents the number of levels and n represents the voltage sources. The number of switches used that can be used for the topology is S equals 5n2, 2, where S represents the switches, and n represents the voltage sources used. 7. Voltage stress. A significant parameter which determines the expenses of the multi-level inverter is the blocking voltage of the power switches as well as the DC voltage sources. If the proposed 8 switching table, utilizing appropriate switching combinations, we acquire the desired output level of the 15 levels multi-level inverter. The output waveform contains 15 voltage levels with inverter requires a variety of blocking switches, then the cost of the inverter is too high. The voltage blocking depends on the topology of the inverter. Power switches are used to open and close a circuit. At the point when a circuit is opened, current moving through it is interfered. Change in current with small change in time, d/dt, will be very high. This causes the switches to melt or fuse. The maximum voltage that each switch experiences at its off state without being damaged is called voltage stress. The voltage stress across each switch is given in the below switch corresponding voltage stress. S1 V1 plus V2, S2 V1 plus V2, S3, S11 V3, S4 V2 plus V3, S5, S12 V2 plus V3, S6, S13 V1 plus V3, S7 V3, S8 V3, S9 V1 plus V2, S10 V1 plus V2 plus V3. Both positive and negative half cycles along with a zero level. Switching sequence for the proposed topology is indicated the underneath table 1. V1 equals 1 volt, V2 equals 2 volt, V3 equals 4 volt, 1 equals turn on and 0 equals turn off. Table 1. Switching sequence for the proposed topology. 9 simulation results. In this paper MATLAB/SIMULINK is utilized for simulation. In SIMULINK the 15-level inverter circuit is simulated and result of output voltage and THD are shown in following figures. The output waveform has 7 levels in both positive and negative half cycle that include 0 level that happen twice in a cycle. This voltage level are achieved with the help of 3 asymmetric voltage sources. The simulation results for the 15-level multi-level inverter is shown in the Figure 3. Fig 3, simulation result for the 15-level multi-level inverter. X total harmonic distortions. Fig 4. FFT analysis for proposed topology. The circuit simulation is done in MATLAB and the output 11 comparison of THD for different current waveform is analyzed for THD utilizing FFT carrier waves method. From the Figure 4 we can conclude that the number analysis which was done for different carrier waves such of harmonics present in the output and the THD is found to as triangular, trapezoidal, ramp and sawtooth and reverse be 2.79% for the fundamental frequency OF50Hz. Fig 5. Comparison of THDs for different carrier waves. The following chart provides the analysis of THD% for above simulation using different carrier waves at a fundamental frequency of 50 Hz. We can conclude that the SPWM technique using triangular wave as carrier wave seems to be efficient. It is because the THD and harmonic elimination for the triangular wave is less as compared with the other waves as carrier signal. 12. Comparison of THD for different modulation techniques. Analysis is done for different modulation techniques with triangular wave as carrier and sine wave as reference for a fundamental frequency of 50 Hz. The following chart provides the analysis of THD% for above simulation. From the above analysis we can say that the scheme of SPWM pod provides lower THD as compared to other two of the SPWM technique. 13. Comparison of third harmonics for different carrier waves. One of the significant impacts of power system harmonics is to increase the current in the system. This is simply third. Because of the harmonics which causes the sharp increment in zero sequence current and this leads to increase in the current of neutral conductors due to which overheating of neutral wires, windings, losses in power. Third. Generation and transmission. Harmonics for various carrier waves of triangular, ramp, sawtooth, reverse sawtooth and trapezoidal at a frequency of 50 Hz is done. Fig 7. Comparison of third harmonics for different carrier waves. Third. Comparison of harmonics for with different carrier waves with sine wave as reference for fundamental frequency of 50 Hz. From the analysis we can conclude that third harmonics are much lower in triangular as carrier wave. Third. 14. Comparison of harmonics for different modulation techniques. Here analysis is done for 50 Hz for sinusoidal pulse width modulation techniques using triangular wave as carrier, out of which third harmonics are much reduced in SPWM apod technique. 15. Conclusion. A new topology has been proposed for the 15LEVEL asymmetrical multi-level inverter with lower THD. They are broadly satisfactory for power application ranges in medium and high power due to their advantages. The main purpose of MLI is to provide limit over the total harmonic distortion, THD, electromagnetic interference, ME, voltage stress on the switches and dV/dt problem, and hence it is mostly preferred in recent concepts due to its benefits. SPWM technique used for producing low total harmonic distortion without the usage of the filter. The simulations are done in MATLAB/SIMULINK. Here the output has maximum output voltage of 7V for DC voltage values of 1,2 and 4V respectively. For practical load purpose the DC voltages can be adjusted to get 230V. From the FFT analysis we can observe that the total harmonic distortion, THD, is obtained as 2.79%. The simulation and experimental results show that the THD of the proposed inverter is considerably alleviated. 16. Future scope. The number of levels got by this topology can be reached out by increasing the number of voltage sources. The THD of the output diminishes for expanding the number of levels. By combining the single-phase subsystem of 15-level multilevel inverter topology to 3 subsystems we can develop a 3-phase subsystem to run motors.